Okay, let's start. So today we are going to learn a new topic, test oracle. So this is our outline today. We will first go through an overview of test oracles, and then we will learn some specific types of oracles. And in particular, we are going to learn some testing techniques related to the design of oracles. And you may have encountered these terms before, and today we are going to learn them. And we are also going to address sanitizer in detail today. So first, let's start from something we have learned before. So in lecture 8, for test scaffolding, we have learned this. So this is a test scaffolding code. And this is an actual implementation of this test scaffolding structure. And remember, in this structure, we learned test oracles. And we mentioned that we will learn more later, and we are going to learn it today. So you can see in this piece of code, we have some assertions to check the value of the function, the return value of the function we would like to test. So this is actually considered as an oracle here. So let's learn what is exactly test oracle today. So here, let's start from the definition of test oracles. So tests, remember in our introduction lecture, we have learned that tests are actually sequences of stimuli and observations. We care about the input and outputs. So it's basically input from an input to an output. So a test oracle normally looks like this. So from the assertion we have learned just now. So it's actually, we need to care about the expected value or the expected output. And normally this is considered as test oracle. And here is a more formal definition for test oracles. So if software testing is considered as a sequence of activities like stimuli and observations, then this oracle is a predicate that determines whether a given sequence is acceptable or not. So an oracle will respond with pass or fail for these pairs of stimuli and observations. It is like a predicate. It is like an oracle orb you may have seen. So it's like predicting whether the result of the test is passed or not. So this is the definition of test oracle. And in verification, an implementation is checked for whether the implementation is aligned with the specifications or not. And for testing, testing is a validation technique. So when we execute a test case, then we check against test oracles. So test oracles and specifications may sound similar to each other here. But, so we may have this question, so is an oracle a specification, or is a specification an oracle? So can you quickly think about yes or no? No. Okay. So the reason is an oracle is not necessarily a specification, but it can be based on a specification. An oracle is actually a mechanism or procedure that determines whether a particular output for a particular input is acceptable or correct or not. A specification is not exactly an oracle, but it could be used to create oracles. So specification is more like a description for the desired behavior of the system. It is it is not that particular to some specific inputs or specific implementations. So in short, oracles are actually the mechanisms used during testing to verify the correctness of the execution. And specification are actually descriptions for the intended or desired behaviors of the program. So oracle is more specific, and the specifications are actually somehow more general. And there are some key components for test oracles. So the first one is oracle information. So this is the information used by the oracle to verify the correctness for the implementation. And it is considered as a specification, but this specification here is double-quoted. It's not the specification for the requirements. So it is more like the oracle information is more like a description or specification that could be used directly by the testing code. And then we also need to have oracle procedure. So once we have the information that could help us to check the correctness of the code, we have to somehow use the information. And the code using this information is considered as an oracle procedure. And normally it could be as simple as a check for equation. So whether the actual output equals to the expected one. And normally oracles are code. So, but of course we can do it manually. We can do the correctness checking manually. But normally we want to do it automatically. So oracles are code, and code must be developed by the developer, right? So, like the project, the actual implementation of the system or the project code, it is built from or derived from the requirement specifications, and it is similar to the implementation of the actual system. It is subject to the interpretation by the developers, and similar to the actual implementation, it may contain bugs. And a faulty oracle could be troublesome because it may introduce false positives where the test cases, where the test is passed, but the actual system is, the actual implementation is faulty. And there could also be false negatives where the tests failed, but there's no fault in the system. So how can we, so just now we learned that, okay, Oracle is implemented as some pieces of code, and its correctness is important. So we have to somehow verify or validate oracles. And of course, like the implementation of the system, verification and validation can be performed on oracles. So we need to check that the oracle conform to the specification it was built from, and we could write tests for oracles. And this will lead us to a circularity problem. So we build the code or the test to judge the system, and then we build the code to judge the judge, and then we need to build the code to judge the code to judge the judge. So this is a circularity problem, and we can't do this recursively. So what we should do is, normally when we design a test oracle, we should have some lightweight verification process. For example, we can do a manual code review to check the correctness of oracles. And there's a design issue with test oracles. So because we need to check the correctness. So actually, normally people are good at coming with new test inputs. For example, if we have a program, if we have a function to calculate the Fibonacci value, and it's easy that we come up with test inputs because we can use the rules we have learned before, like boundary value testing, like the equivalent class-based test case design. So it's relatively easy to come up with new test inputs, but it is much harder to automatically check the expected or correct or desired result. For example, if we want to test the correctness of the input 100, we need to know the exact value or the expected output of this function. And this is sometimes tricky in real world cases. So it's much harder to automatically generate the expected result. And most commonly, we have to write the test oracles by hand tied to a particular input, tied to a particular test input. And we have to somehow get the correct or desired value manually. And this requires a large amount of manual effort. But luckily, we do have some low effort test oracles which don't require too much of coding, so we don't have to do everything manually. We can come up with some test oracles that could be derived automatically. So talking about the costs of building test oracles, there are some trade-offs when we build them. So if we want to build them automatically, we have to sacrifice something. And there are several trade-offs we must consider when we try to build test oracles. We can specify the exact output behavior from the system. So the keyword here is exact. So we can, of course, given a particular input, we can try to come up with the exact output behavior or the exact expected behavior. However, this is very hard to do for more than one test at a time because we have to do it multiple times for every test input. Or we can trade. This is very precise because we are manually designing the expected output for a particular input. Or we can trade this precision for generality. So we can come up with some test oracles that could be applicable to multiple test inputs. So we can do this by specifying the properties that should be obeyed by a function. And we can also try to build a model for a function. And we can also try to check for types of anomalies that our programs can suffer from. For example, maybe in some function designs, like in some C programs, a function should return 0 if it succeeded. So we can check for the return value. And we can also check for crashes. So normally a function shouldn't crash when it executes. So these are but this is less precise because we cannot locate the exact reason for the crash. But we do know there's something bad happening if it crashes. So we are trading precision for generality. And talking about trade-offs, we need to consider different properties of test oracles. So a test oracle is complete if it can offer a verdict for any set of test inputs. And a test oracle is sound if it can offer the correct predicate for any test case. And a test oracle is correct if it is both sound and complete. But it is very hard to achieve the correctness here. And we can have, normally we need to have partial correctness or partially correct. So which means that the test oracle is sound but not complete. So given these properties, we can come up with some metrics to judge or justify the quality of test oracles. So we need to consider about the criteria to use. The first criteria is the cost to build the test oracles. And we should consider the cost per test and overall cost. So this is related to the question of how much effort goes into building this test oracle. What we want is we want low cost here. We want to lower the cost. And the second one is related to soundness. So it's actually the accuracy of the verdicts of the test oracle. So we should think about whether this test oracle will give us the correct answer or the wrong answer. And we want high accuracies. And the last one, of course, is related to completeness. So can this test oracle be applicable for multiple different test inputs? And what kind of situation does this test oracle works with? So we want high completeness. And derived from the properties, we could have different types of test oracles. So the first type is specified oracle. So this is mostly done manually by the developers. So the developers can use the requirements to formally specify properties that the correct behavior, or to describe the correct behavior of the system. And the second type of oracles is called derived oracle. So an oracle is derived from, could be automatically derived from the development artifacts or some program executions. So this is more like the automatically generated test oracles. And we could also have some implicit test oracles. This is to summarize some properties that is expected for many programs. For example, the crashes of the programs. And lastly, we can always fall back to human judgment or human justification for test oracles. So let's learn them one by one. The first type of oracles we are going to learn is the specified oracles. So specified oracles judge the behavior using a human-created specification of correctness. And this is an illustration of this type of specified oracles. So basically, we just prepare an expected output according to a particular test input. And after we have executed the program on the test, we can compare the actual output with the expected output. And this expected output is derived from the requirement specifications manually by the developer. So most oracles we have encountered are actually specified oracles. And actually for almost any manually written test cases, we use a specified oracle. For example, in the example we have encountered, these two asserts are specified oracles, so they are manually derived by the developer. And you may notice that this calculator sum 1 and 2 equals to 42, and this sum minus 1 and 1 is also 42. So do you know why it is like this? This should be 3, right? This should be 0, right? Why we put 42? It's because of the stub here. We use in integration testing, we can do stubbing, and this stub here returns 42 as a dummy behavior. So when we design the test, we use 42 here. So it's manually specified by the developer. And talking about specified, the simplest form of specified oracle is called an expected value oracle. It is the simplest. So we just need to specify the exact value for a given input. For example, for this, we can for the function calculating the max value for any two integers, what we can do is we can specify the expected value according to the semantic of this function. And then we can do this assertion to check whether the expected value is correct or not. However, there are some limitations of the expected value oracles. So usually they are not reusable because they are attached to a particular test input. And sometimes we need to think about how can we extend this to multiple tests. So can we derive some test oracles that are applicable even if we change the test inputs? Do you have a question? This is one of the specified oracles. So you can see we are under the section of specified oracles. So this is a particular type of specified oracles. So this is actually quite limited because it is very precise, because we can manually come up with an expected output for any given input. But it is not. But it lacks completeness. It is not reusable. For example, if we change the test input from 3 to 9, maybe we need to change the expected output here. So it is very specific to the test inputs, and it is not applicable if we change the input. So we want to consider to increase the completeness here. And what we can do is we can use some self-checks in the program. So rather than comparing the actual values, we can use properties about the results to judge the sequences. And this idea is a little bit similar to what we will learn later today, to the concept of metamorphic testing. And here is an illustration of this self-check. So instead of generating an expected output attached to this test input, we could derive some self-checks and put them into the program under test. And these self-checks will report error whenever it encounters some issue. So it normally takes the form of assertions. And here is an example. For example, if we, in this multiply function here, normally the implementation is just we calculate the multiply of A and B and return the result. But what we can do is we can add some self-checks which are applicable to regardless of the test inputs. For example, any integer multiplying 0 will end up in 0. So we can add a test. We can add an assertion according to this property. Or if both of the values are positive integers, then the result should also be positive, right? So we can also use this property to derive another assertion here. So we can add some self-checks like this into the program under test, and they will, if we have implemented the program with errors, then they will notify us about failures when we do testing. So this is the idea behind self-checks. So we can use some more common properties of the program to do this correctness checking. And you can see that this is not as precise as the expected output checking. because we are not checking a particular value of C here of the correct result. We just use some general properties, and the program could still end up in error even if it reports no error during self-checks. But we are sacrificing precision for generality. So this is like a trade-off here. And talking about trade-offs, we need to think about the design of these self-checks. And they are normally written at the function level. So we want it to be general, so we want to use some high-level features of the function to design these kind of self-checks. And it is mostly desirable to work for any input to that function. And however, this is also there are some limitations for this type of self-checks. Just now we mentioned that they can only check the properties we have introduced, and they are not able to fully cover to fully check the correctness of the function. So the accuracy or the precision here is somehow sacrificed. And if we want more properties, if we want a higher accuracy, we need to introduce more properties to check. And it also means that we are increasing the cost of developing these test oracles here. So everything is about trade-off. And another type of specified or test oracle is that we can use system models as test oracles. And like levels of testing, we do have levels of oracles, and we do have system level of oracles. And in lecture 8, we have learned model-based testing. And this is a link you can click on, and you can it will lead you to the slides related to model-based testing. And in model-based testing, we learn about different models that could be used to describe the system under test. And in that, and those models to derive test cases could also be used to derive test oracles. For example, we can use the actions in the decision table to design test oracles. So we can check whether the actual output of the system matches the action in the decision table. So this is quite obvious. And if we model the entire system as a finite state machine, we can also try to use the error states to check if the program runs into some errors or not. So that's all about specified oracles, and they are mostly done manually. And we want to automate things, so we care more about the derived oracles, which could be derived automatically from the program. So derived oracle is defined like this. If no specified oracles exist, we can try to automatically derive them from several different sources of information. So the first source is the project artifacts. So we can try to derive test oracles from the documentation of the program. We can try to reuse existing tests, and we can also try to use other versions or implementations of the same system or the same design. And we can also derive test oracles from the program execution results. We can try to detect invariants. We can try to mine some specifications. So the first type, or the first technique to derive test oracle is called differential testing. So this is the definition of differential testing. Differential testing is actually to detect bugs across or inconsistencies between multiple different implementations or multiple different versions of the same design. And it is very useful if we don't have an automated, if we don't have an existing specified oracle. So here are the steps to do differential testing. So first, we need to select variants of the design of the system. So the variants could be different versions of the same program. So you can use version 1, version 2 and do the comparison. And we can also try to use entirely different implementation of the same program or the same system. For example, we can, for C compiler, we do have GCC and we do have C-lang, right? So we can have multiple different programs doing the same task, and we can use them as the variants here. And for another example is the database, SQL database. There are multiple different implementations of SQL databases. For example, we have Postgres SQL, we have MySQL, and we have other implementations. They are essentially doing the same thing. So we can use them together as the variants here. And once we have selected the variants, we can then generate the test inputs to test them. And this designing of the test inputs, for the design of the test inputs, we can use the previous methodologies we have learned. And we can also use fuzz testing or fuzzing. So differential testing is not, so it is also called a testing technique, but it is only related to the oracle design. So it could be used together with other testing techniques. So once we have selected multiple versions or multiple implementations for the system, we can derive test inputs for them. And after that, we just execute the variants with the inputs we have generated. And then we just compare the results and analyze the differences. So for example, if we set up the database with the same data and we run the same query, both Postgres and MySQL should return us with the same result, right? And if they return us with a different result, then it means that one of them must have been implemented wrongly. Another example, like for compilers, if we have the same C code before compilation, and we compile it with different compilers, and we run the compiled programs, and if the compiled programs gives us different results, it means that one of the compilers must have been implemented wrongly, right? So there must be some inconsistencies or some problems in one of the variants here. So this is the idea of differential testing. So we check the correctness by comparing the execution results of similar programs. And you may think that, okay, this is very simple. So we just compare the differences between similar implementations. So, but what can we do in deep? So actually comparing the results and analyzing the difference is not very trivial most of the time, because for the compiler or for the databases, we don't just want to compare the final result most of the time, because if we just compare the final result, we may not be able to expose some errors in the intermediate steps. But since they are different implementations, how can we match the intermediate steps automatically and check and do the comparison? This is actually very hard. So we can do a lot of research in this last step here. So that's all about differential testing. And now let's move on to regression testing. So regression testing is a type of software testing that aims that happens actually after we have updated the software by adding or modifying some features. And this regression testing is the purpose is to make sure that the changes doesn't affect our existing features. So this is the regression testing is defined according to this aim or this goal. So we don't want the updates or modifications of the code to affect our existing already working code. And because we don't want the changes to introduce new issues or regressions in functionality, so this is called regression testing. So this is why it is named as regression testing. And normally this is what we do with regression testing. We just, whenever changes are made to a system, we just rerun our existing tests. And any existing test that has been passed should still pass. And obviously we can use the older version of the program as the oracle here. And this is a typical workflow of doing regression testing. So basically we just identify the changes, and then because we may have maintained a lot of test cases in our system, and then we just try to prioritize the tests related to the changes or the system parts affected by the changes. And then we define the entry point and entry criteria for those test cases, and then we schedule the test. So this, because normally we just rerun the test for regression testing, so we don't need to design new ones. All we care about is if we have a large amount of test cases, how can we prioritize the most important ones? So this is about regression testing. And the last derived testing is called metamorphic testing, and there are some backstories with technique. And the inventor of this technique is called T.Y. Chen, and this is him. And he's currently in Australia, and he's a professor in Swinburne University. And like many valuable research, for example, deep learning, metamorphic testing was not recognized by the academia when it was invented. So people think, okay, this is just some kind of bullshit they don't care about. And this paper, when he firstly proposed this idea of metamorphic testing, he was a visiting scholar in Hong Kong University of Science and Technology, and it was only published in some kind of internal reports of that university. And the academia, they think they don't accept this. They think this is some kind of nonsense. And you may notice that there's a blue edge for this screenshot. You can click on it and access the original paper, the PDF of this paper. And however, it was published in 1998, and it actually starts an entirely new research direction for software testing. And there are many follow-up works for this metamorphic testing idea. And let's try to learn it. What is the magic of metamorphic testing? So metamorphic testing is, so this is a formal definition here, and I have highlighted the keywords. So the definition is also related to test oracles. And the idea is that it actually leverages the metamorphic relations of the inputs between different inputs and outputs. It's like some kind of equivalence or some kind of internal connections between inputs and outputs to check the correctness of the program. And don't worry about the definition. We will learn some practical examples later. So what we do is we transform the input data based on the metamorphic relations we have observed from the system and compare the outputs and try to detect inconsistencies to the relations. And these inconsistencies could indicate bugs. So this is the basic idea of metamorphic testing. And the key here is how can we derive metamorphic relations. This is the key. And we do notice that everything is about trade-off. So we are similar to self-checks. We are actually sacrificing precision for generality here. So let's try to have a look at an example here. So assume we have an implementation for this function to calculate sin x. And it is actually hard to get the expected values for us. So if we don't have the implementation of sin x, it's actually hard to get the exact values. We have to calculate the correct answer using some mathematical formulas. So it's hard to get the expected values. However, there's a metamorphic relation here. So sin x, the result of sin x should equal to the result of pi minus sin pi minus x. So if we design the test input, we have one test input of 1 here. Instead of manually calculating sin 1 and use the expected value as the check here, what we can do is we can try to design a second test input, pi minus 1. And then we compare the results of pi minus 1, sin pi minus 1 and sin 1. And if they are equal, then it means that the function is likely to be implemented correctly. And if they are not equal, it means that there's definitely some error in the implementation of sin x. So this is the idea of metamorphic testing. And just now we learned that we need to transform the input data. And this pi minus 1 here is actually the input data transformation using the metamorphic relation here. So we do also need to notice that we are sacrificing the precision here because we are only checking the results according to this one single rule. So we may have implemented the function wrongly. Maybe we have, instead of implementing it as a sin x, we may have implemented wrongly as cosine x. And cosine x also satisfies this metamorphic relation here. So we cannot detect error if we just use this one single relation. So we are sacrificing precision here. But although we have sacrificed the precision here, we do increase the completeness or generality here because we don't care about x here. For any test input, we can use this test oracle to check for correctness. So this is how metamorphic testing works. And now let's do a live poll. Let's do an exercise. So let's consider a function that sorts an array of integers from min to max. Let's consider this sorting function. So which of the following metamorphic relations are valid? There might be multiple correct answers. Actually, all of them are valid. All of them are valid. And let's go through them one by one. So assume we have this array here. When we try to design the test case, we have this, we design this variable. And after sorting, it should be 1, 2, 3, 4, 5. So the first metamorphic relation is if the array is reversed and passed to the sort function, the output should remain the same. So we can design this test case. And this is using Python. So we can have a reversed array, and we can sort the reversed array. And then we can compare the results. The result should remain the same. So this is the first metamorphic relation. And the second one is, so if we add some duplicate elements or duplicated elements into the array, they should be put into somewhere, into the correct position, and it shouldn't be eliminated. So we should have multiple elements with the same value. And this is because in some implementations of sorting algorithms, they may eliminate duplicates during the sorting. So this is to check the correctness that we have reserved the duplication. So what we can do is we can try to select an element. For example, we can select 2 here, and then we can sort the duplicate array, and then we check whether 2 appears 2 times or not. If there are 2 2s in the sorted array, it means that it has passed this test. And if there are if there's only 1 2 left after sorting, then it means that we may have encountered into some kind of errors. And the third metamorphic relation is if we have another array, where all elements are larger than the original one, and if we combine them together before sorting and do the sorting on the combined array, it should give us the same result as if we sort them separately and then combine them together. So this is what we can do. We have 1, 2, 3, 4, 5 here, and we can have one more array with 6 and 7. So 6 is larger than any previous elements. So we can try to combine them together and do the sorting. This should give us the same result as we sort them individually and combine them together. So this is I have omitted some steps here, but you got the idea. So this is another metamorphic relation we could use for testing. And we could derive many more metamorphic relations based on the actual semantic of the target on the test. So this is actually the idea of metamorphic testing, which is to replace the expected output with some other relations or values between the inputs and outputs. So this is roughly the idea of metamorphic testing. And apart from metamorphic testing, so those are so for differential testing, for regression testing, for metamorphic testing, they are all deriving test oracles from program artifacts. So they are using different versions of the program, different implementations, or they are using some existing tests, or they use some internal semantics of the program under test. And apart from using the program artifacts, we can also use some observations from program execution for testing. And this leads us to the invariant detection. So an invariant is a property or condition that remains true during the entire execution of the program. So we have different levels of invariance. We could have loop invariance. Actually, we have encountered this term before in lecture 6, and you can click on the link to have a look at what we have covered before. And there are also function or method level invariants. So, which means that certain properties or certain predicates should remain true during the entire execution of the function. So, actually, there are some algorithms to automatically detect invariance from program executions. And one of the simplest way is to prepare a set of test inputs that the program is known to work correctly on. And then we can execute the program with this set of test inputs and observe during the execution for the properties that remain true during the entire execution, and use those properties as the invariants. And why do we care about invariants? Because invariants are naturally test oracles. So if we found some invariants that if we have identified some invariants for a program, and those invariant turns out to be false during the execution, then it means that the program must have been implemented wrongly. So that's why we care about invariants, and these invariants could be derived automatically. And the algorithms for deriving invariants could be very complex, so we don't cover them here. But you just need to know that, okay, invariants are another source for test oracles, and they could be automatically derived. So that's all about derived oracles. And let's have a 10 minutes break, and I'll see you later.
Let's get this straight.
All right, let's start the second half of today's lecture. So just now we have covered specified oracles, which are mostly done manually by the developers, but they are somehow accurate. And we also learned some derived oracles, and all these so-called testing techniques are actually related to the design of test oracles, and they could be used together with the test case generation techniques we have learned before. So now let's continue to learn some more general test oracles, which are called implicit oracles. And in particular, we are going to cover the topic of address sanitizer. We have been using it in our practices, but now let's learn how it works. So implicit oracles is likely the most general type of test oracles. So it doesn't require domain knowledge of the program, the specification, or the semantics of the program, and it is actually used to check for the properties that should be applicable for any program. So implicit oracles are often used to detect general anomalies, for example, for network irregularities, for crashes for programs, or deadlocks, or infinite loops, things like that. So these are the faults that do not require expected output or the semantic relations between input and outputs. So they are very general. And although they are very general, we need to somehow think about how to enhance the sensitivity of detection here. So one of the most popular approach of increasing the detection sensitivity is to use sanitizers. And address sanitizer is one of the most popular one. So address sanitizer is a compiler and runtime technique that exposes hard to find bugs with 0 false positives. So it is, you can see some of the keywords here. It is a compiler technique, which means that it actually tries to instrument the target program during compilation. So we have learned that AFL, or American Fuzzy Lob, tries to do instrumentation during compilation, and address sanitizer works similarly. So it tries to instrument the target program during compilation and during execution. So it is also a runtime technique, because during execution, the instrumented code will work to capture the failure of the program. So these are all the different types of failures that address sanitizer supports. So there are some most significant ones we should take note of. So double free and use after free, because these two types of vulnerabilities or bugs are more exploitable for malicious purposes. And of course, it can also try to detect variable overflow, buffer overflows, and also some other issues. So this is the basic mechanism of address sanitizer. So first, it tries to instrument the target program during compilation. And what the instrument does is to replace the malloc and free functions. So there are actually a set of functions that can allocate a piece of memory for the program, and address sanitizer will replace these malloc and free functions with a customized version of these allocation functions. So it still does the allocation functionality. So it still helps the program to allocate the function, the memory just as a normal malloc function, but it is controlled, or it is modified to work a little bit differently. So the difference is, so this replaced malloc function will try to mark the memory around the allocated regions as write zones or as poisoned. So whenever the allocated region, the write zone or the poisoned memory location is accessed, access means read or write. So whenever the write zone is accessed, it will report an error. So this means that this instrumentation will try to isolate or to surround the allocated memory with write zones. You can imagine this. This will incur extra memory cost, but it actually helps to capture. It actually helps to capture the errors very accurately. We will see that later. And the freed memory is placed in quarantine and also poisoned. So this means that whenever we try to access a piece of freed memory, we will end up in error again. This actually, by poisoning the freed memory, actually it helps us to detect double free or use after free. So if we try to reuse a pointer that has already been freed, then we will end up in error because the freed memory is poisoned, is marked as a write zone. And these are the functionalities of the replaced malloc and free. And then address sanitizer will insert code to check if an address access is poisoned or not. So if the program is trying to access a poisoned address, it will report errors and stop the execution of the program. So this is how address sanitizer works. And this is a basic mechanism. It is much more complicated. And the most difficult part of this is how to check this fastly without affecting the program's execution too much. So there are a lot of optimizations, there are a lot of work behind. But we just need to know the basic mechanism here. And address sanitizer is very, very easy to use. We just need to add this flag, compiler flag, during compilation, and then we can use it. So this is a report. So just now we mentioned that it will report error whenever the program try to access memory in the write zone. So this is a report, and you can see that there are some highlighted parts of the in this report. So you don't need to know all of them, but you just need to know some key points. So the first one is, we can observe here, is it actually helps us to check the type of error here. So in this report, we can see that this bug is a global buffer overflow bug. And the second type of information is that we can get more information of the bug type. And this is, we can see that this is a write out of bound for 4 bytes. So this is the second piece of information we can get from this report. And then if we have some debugging or symbol information during compilation, we can also get the exact location of where the bug happens. So this means that the bug happens in this file, in the main function, at line 7. And the last one is the out of bound write is related to the global variable x, and this x is located in this file, line 3 at column 8. So it actually helps us to get a lot of information about the bug. And you can get more details from some online materials created by Google and Microsoft. And let's try to do a live demo for address sanitizer. So we were always talking about address sanitizer can increase the sensitivity of the program, but how exactly does it look like? How exactly it works? Let's have a look at this example here. So if you have a Linux environment, you can also try it on your own. So you can follow these steps. So let's have a look at this program here. So in this program, we are trying to allocate a piece of memory with the size of 5 integers. So it's actually 20 bytes. So this array has 20 bytes. And then we assign values to this array, starting from 0 all the way up to 40. And then we can print out the element at the index 4, which is the last element of this 5-element array. And after that, we can do an out-of-bound read. So index with 5 is actually out of the bound of this array. And we can read it. We try to read it and print out the value of the memory slot after the 5th element of this array. So this is actually an uninitialized piece of memory. So we may encounter whatever content, we may print out whatever content in this piece of memory. So, and after that, we just do a free of this allocated memory. So let's try to compile this. Let's try to compile this program with and without address sanitizer and observe the differences during compilation. So this is the C program we just mentioned. So we are trying to read 1 byte of this array. And let's try to compile it. Okay. Let's try to compile this program without address sanitizer. And name it as test-raw. So if we execute this function, normally it won't crash. In some very rare cases, it will crash. So you can see here, we can print out the element at index 4 correctly. So we are storing 0, 10, 20, 30, and 40 into this array. And we can successfully print out the out-of-bound element, which is the 6th element of this array. Because normally reading out-of-bound is allowed by the system. But there are some errors in the program, of course. So let's try to compile this program again with address sanitizer. So what we need to do is we just need to add this flag, fsanitize equals to address test.c. Let's name it as test ascent. And then if we execute the program, we can see we ended up in some errors. If we print out the signal of this execution, you can see it's 1, it's not 0. So the program ended up in some errors. And this error we can see it's a heap buffer overflow. So which means that this overflow happens on the heap, not the stack, not global variables. And we can also see it is a read of size 4. So you may wonder why it is read of size 4. We just read one more element, right? Why it is size 4? Do you know why? Because it's an array of integers, and each integer has 4 bytes. So we are reading 4 bytes out of bound. So this is read of size 4. And we can clearly see that you can see that it's a little bit you can see it's a little bit different from the example we have seen in the lecture notes. We don't see the exact line number here. That's because when we compiled the program, we didn't add debugging information. We didn't add the symbols into this program. So debugging symbols. So if we want to locate the exact location, we need to do this during compilation. We need to add the flag. We need to add the flag to this -g to include debugging symbols. And if we run this program again, you can see that we still don't get didn't get this. Okay, this is weird. But maybe this is due to the version of this address sanitizer. But normally it should be able to print out the line number here. And this is, as you can see, this is particularly useful not only for debugging but also for capturing errors. So it actually helps us to do debugging. So we know exactly what happens, what kind of bug is happening here, and we know roughly where it happens. At least we can get the call stack for this error. And the program actually, if we don't add this address sanitizer, the program will fail silently, or it will run into some errors or problems without getting notified. So when we do testing or when we do fuzzing, if we don't use address sanitizer, we may miss out the bug of reading out of bound just now. So this is why we are interested in address sanitizer, and it is actually practically useful. So we just need one single compilation flag to capture all these bugs, So that's why it is a very, very useful technique. It is a very, very useful technique. And it is very general, so we don't need to put too much of efforts, and we can capture a lot of bugs. So it's a very good implicit oracle here. And the last type of oracle we are going to cover today is called human oracles. So if in some cases we can't easily do automation. For example, for some programs with very complex graphical user interfaces, we may need specific techniques to do the testing. And we can hardly do test scaffolding in those cases. And we have to involve human as the judge to check whether this program has executed correctly or not. It is not ideal, but it is surprisingly common in practice. And normally, if you don't do testing, if you don't write tests, you may need to check for errors manually. And it is recently using humans as oracles become particularly popular. And can you think about an example or a real-world case of why recently it has been very popular? No? Okay. Because human feedback for large language model alignment is very popular. So for example, for OpenAI, when they are trying to align the large language models to regulate its behavior. So for example, ChatGPT, it shouldn't teach you how to rob a bank, right? So how do they prohibit these kind of behaviors of these large language models? They can't, the output of the language model is very random, and it covers a large range, and it's very hard to design automated test oracles to test whether this large language model has reaching the right zone or not. So they hire humans to align the model, to mark the output of large language models as regulated or not. So that's why human oracles, although it doesn't sound very fascinating, it's not automated, but it's still very useful. And there are some, and for big companies, they are actually crowdsourcing these oracle marking tasks. And there are some famous services or platforms to do this crowdsourcing of test oracles. So for example, the most famous one is Amazon Mechanical Turk. And of course, we have some other alternatives here. So these companies, they outsource this oracle marking because they can do it with lower costs. So that's all about today's content, and let's have a recap of what we have learned today using this outline. So first, we have covered an overview of test oracles, and basically test oracle is a predicate of whether a test is passed or not, and it is used to check the correctness of the program execution. So that's why it is called an oracle. It is like an oracle orb. And test oracles, although it sounds similar, or it behaves similar to specifications of programs, but they are actually different. So test oracle is more like a specific check for particular test inputs, and the specifications is more like a higher level of descriptions of desired behaviors of the system. So that's about the basics of oracles. And of course, when we design oracles, like many other things, we need to consider some trade-offs. We need to consider the cost for designing these oracles. We need to consider the accuracy or the precision of this oracle. And also we need to consider the completeness or generality of the oracles. And we could have, and then followed by the idea of different properties of oracles. We do have different types of oracles. And we have, the first type is specified oracles. We can use the simplest way to do expected value checking. And of course, we can also try to move the checks into the program on the test to do self-checks for the program. And in the test case, we just need to check for the We just need to check for the failures or exceptions from the self-check. And these are specified oracles, and they are, and of course we can also use system models as oracles. For example, we have learned decision tables. We can use the action and the actions in the decision tables as test oracles. So, but the advantage of specified oracle is that they are mostly very precise, and but the drawback is they require a lot of manual effort, and they are mostly done manually by the developers. And we have some automatically derived oracles, which are called derived oracles. So we can derive test oracles from program artifacts or program execution results. So there are several testing techniques related to deriving test oracles from program artifacts. For example, for differential testing we can try to collect variants of different versions or different implementations of the same functionality of the same program, and we execute them together with the same set of test inputs, and then we compare the execution results. If the results are different with the same input, then there must be something wrong in one of these implementations. So this is the idea of differential testing. And then we can also do regression testing, which is mostly focused on testing the newly updated features. And we can reuse existing test cases to do regression testing. And the key of regression testing is to do the scheduling, because we may have a lot of test cases to do this regression testing. So we need to schedule and prioritize the most important ones. And for metamorphic testing, it is another technique to derive test oracles from based on the semantic of the target program. So we need to derive some metamorphic relations according to the input and output relations of the target program. And there are some interesting facts about this metamorphic testing. The inventor is currently in Australia now. And apart from deriving test cases from program artifacts, we can also try to derive test cases from program execution results. We can do invariant detection automatically, and invariants are naturally test oracles because they should remain true during the entire execution. And if an invariant becomes false during the execution, it means that the program must have been implemented wrongly. And the advantage of the derived oracle is that it is more general. So we could use the same test oracle for multiple different test inputs. But it is still specific to particular programs. So it's not so general. It is still attached to programs. So the most general type of oracle is called implicit oracle. So it is applicable for any program, and normally we just observe for crashes, we observe for anomalies during the execution. And in order to do this with higher sensitivity, we could use different types of sanitizers. And one of the most important or popular one is called address sanitizer. And we just learned the basic mechanism of address sanitizer. And we also showed with a demonstration that it could indeed increase the detection sensitivity. And the last one is, nowadays, because of the popularity of large language models, we may involve humans as oracles, because there are always some systems that could hardly be tested with just code. So that's why we need human oracles, and we can do some outsourcing of human marking tasks in some platforms. So do you have any questions? Specification mining, okay, that's a good question. So specification mining, I think is a little bit out of the scope of this course. So there are some advanced, actually this my research admin is doing some specification mining task research. So we can, so given a set of test input and a set of, and the observed output of the program, we can try to observe for the relations between the input and output to capture the specification of the program. And the specification we captured is normally not as high level as the requirement specifications. It's more like some low level properties of the program. For example, there are some points to specifications, which means that we want to know whichever pointers are aliases of each other. We can use test inputs and outputs to infer the relation between those pointers, things like that. So there are some low-level specifications. So, but that's a little bit out of the scope for testing, so we don't cover that. And do you have any other questions? Okay, that's good. And we will release the result of assignment 1 tomorrow, and the specification of assignment 2 probably this weekend. We have to do it this weekend. Okay. Okay, that's all. Thank you.
your assignment? Done?
No.
I believe the submission is on Monday, yeah?
Yeah.
Yes. still have time for that, right? So I will ask if you guys can like do it separately, or do you combine or like join online? Can you join online at the same time by any chance? During the tutorial time. Your presentation is on the 20th of November, right? Yeah.
So it's necessary that both of us.
It's because they can learn individually. So either join the presentation. I'll confirm it with Cici and let you know. Yeah.
Or because I just need the information as soon as possible because I have to like.
All right. How many people?
Sorry.
How many people will be here and how many people will be online?
I will have like group of 2.
Okay. And just for one of